Hello and welcome back to Calculus 1, section 3.2. We're working with derivatives today. So one procedure to find the derivative. Then we have a concept of what the derivative is used for. And now we want to see how to work with derivative. What is the meaning of the derivative in some extent as well. I'm going to again state that derivative measures the change. What kind of a change? Any kind of a change that can be mathematically, well, all kinds should be mathematically modeled, and derivative is the one that detects the change. Doesn't matter how minute or major that change is, the derivative will measure it. If we are talking about the change of population, the growth of money and a bank account, the spread of the oil in the ocean after the accident, or modeling the spread of the disease, or technically anything, including the internal organs. So in terms of, I don't know, the growth, the weight, and everything else. So derivative measures the change, and when we are focusing on the two-dimensional environment, which is our Cartesian XY graph, we might have the function f of x, and for, let's say, particular region A to B, we are going to observe the piece of the function. We are going to notice that that piece is increasing. We're going to notice that there is, for that particular piece, if you draw a little triangle here, there is delta x, which is change in x, and delta y, which is change in y. So the hypotenuse of that triangle could be understood as the good approximation of the function, could be understood as the tangent line to the function, and it shows either a growth or decay of the function over that interval. So we can use the derivative to show that the particular function is increasing or decreasing. We can show something called concavity, which we are going to visit in chapter 4. So now, if you are observing the rules of differentiation, what I wrote in blue up there, that derivative measures change. What would be the value of the derivative if I say there is no change in the function? What is it? 0. So if there is no change in the function, the derivative has to be 0. And then if we have a constant growth of a function, we are going to have a constant value for the derivative. So we can say verbally now, but we're going to have a formula for that next time, that if there is no change in function values, the derivative is 0. So that means graphically that if I have a function f of x equals to 2, which is just this horizontal line, the derivative of that function is 0. Which is just the x-axis in that case. But then we might have more interesting function. Say it goes like this. So let's say this is our f of x now. Now if you really want to find the equation for that function, you can, because all of these are linear pieces, so it's easy. It's going to be a piecewise function with the 3 pieces. They're all linear. But to discuss the derivative, we actually don't have to do that. We can just look at this and immediately draw the graph for the derivative, because all of these linear pieces are easy to deal with. We have the first piece, the increasing piece, and what do you think would the derivative be for that piece? 1. Very good. So derivative would be 1 up to the y-axis. Why is it 1? It's the slope of the black line. Slope of the black line, which is a linear line, is 1, because you can see it goes 1 square up, 1 square over, 1 square up, 1 square over. So the change is 1, because 1 divided by 1 is 1. Now, how about the next piece, the flat piece? 0. So we have now on x-axis, we have a 0 there. And how about for the rest? -2. Why is it -2? The slope of the third piece is -2. So you see that it's a slope. Now, didn't we describe the tangent line to be the slope? Sorry, the derivative to be the slope of the tangent line. So all of these lines will have a slope of 1 and then 0 and then -2, and that's what the derivatives are. Now, all of this becomes more interesting, obviously, when we have curved functions. But for right now, we're observing simply the slope of each piece, and we draw the graph. Now let's see what happens as the function curves around. So what happens in this case? We start by first figuring out where we have min and a max, because the tangent line at those values is horizontal. So what would be the derivative at those points then? 0. Because the derivative of, that's very good, the derivative of horizontal, the derivative of the slope of the horizontal line is 0, and the slope, and the line over there, the slope, is the derivative. So we start these like that. And now we look at this and we say, do I draw the derivative to the left of the first point going up or going down? So it's one or the other. Can't have both. And we have to figure out which one to draw and which one to erase. Now, if you think about this, all of the slopes to the left, all of the slopes to the left of the red point are positive slopes. All of them. So what should I draw? Above or below the line? Above the line. Very good. Because all of these slopes are positive, so the derivative has to have positive y values because the function had positive slopes. Now, if you look in between the 2 points, in between 2 points, all of the slopes are negative, which means that now it should fall. And then if you look at the right, it goes up again, the slopes. So we are looking at the parabola graph there. So questions like this, you start by figuring out where the extreme points are, min and a max. And those are zeros on the derivative. Because at the maximum value or a minimum value, you are going to have horizontal tangent line, and every slope every time for a horizontal line is 0. So that's why the derivative is 0 at those points. And then you do the simple analysis of the rest. What's above and what's below. So let's see. And I'm going to write also this as a rule. Vertical asymptotes, vertical asymptote locations are preserved. So that means that if the function had a vertical asymptote at 1, the derivative must have the vertical asymptote also at 1. So let's have an example that has that as well. Let's see if you can draw the derivative for this piecewise function. See you next week.
Great. Let me ask you a question. Do you think it's true if you study at night, you remember it more?
Not necessarily.
Me and Dan were talking about that today.
It's a quality study time, so the brain can absorb for just so long.
Yeah.
So if you study for 6 hours continuously, it's just a waste of time.
Yeah, pretty much.
Most likely you're efficient for 2 or 3 hours in a shot, and then you have to take a break and do something else. Yeah. And then maybe an hour, 2 hours come back. That's why students who set out a block of time of 5-6 hours on Sunday to study 40 exams, or actually any study in 40 exams is highly inefficient and
no, I do like an hour and a half.
Whatever
15-minute break.
Yeah. Whatever is everyone is different.
Yeah.
But you're not gonna find anyone who's gonna sit longer than 2-3 hours in a shot and retain information. People usually say, well, I study. Well, yeah, I walk every day. That's not equivalent to running. So I'm not gonna go run in Olympics. You know what I mean? That's and then another thing is reading math problems and observing others do problems, which is also a waste of time because you're not sorting the information actually when trying to figure it out. It's like trying to learn how to drive while watching others drive. So you've seen a NASCAR race, and you just think, okay, I got this, right? And you just go down and die. But that's how it is. It's, everyone wants to be people like to dream of being something rather than being something, because achieving that takes time, effort, discipline, and it's so easy to see someone who's successful in anything and say, okay, I want to be like that person, which is just nonsense because you're doing nothing to be. That person worked 20 hours each day. And yeah, a lot of people say, oh, it's easy, Musk has money. Of course he has money, he made the money. He was sleeping in the office, he didn't own an apartment. He rented office instead of the apartment and lived on a couch and coded all night long for years and read the books and studied engineering and
he did crack too.
No, he didn't.
That's what someone said. There's like an interview.
See, that's because that's the same nonsense like they say that Einstein was bad in math, because that people feel that they are closer to Einstein if he was bad in math.
Yeah.
Have you seen Einstein's field equation?
Yeah.
It takes 2 years just to figure out mathematics that leads up to understanding that equation, let alone to use it later on.
Yeah.
So people come up with all these stupid stories to kind of bring these brilliant people down to closer to their level because they're not incapable. Everyone is capable of something. You just either didn't find it, or you have no discipline or will to actually put in. This understanding of reality I have because I know Olympic runner. That's why.
To add to what you're saying, I'm not sure if this is entirely true, but the first time something's done is the hardest thing ever. Every time after that, it's simple. Like the Manhattan Project, split again was a whole big thing. Nowadays, we do it on a whim for energy.
Yeah, that's true. And every time, first thing to discover. But imagine the amount of knowledge and effort and energy that you have to put in, right?
Yeah. To
do something new. And then after that, everyone follows, and it's easy to replicate, and it's easy to. So, people say, oh my God, the celebrities and the actors and so on, because most of the people see is their end product, which is a movie that is 2 hours long. No one sees the training for 6 months that they had to go through. No one sees the, a year of filming, and no one sees the the skill that it involves. It's just, oh yeah, he has money and crazy cars, and then he's, he has this movie, and the movie is an hour and a half long, so, it's easy life. It's not. If it was easy, everyone would be doing it.
Yeah, true.
So, yeah, it's the sad reality that, everyone just wants to be something and not doing anything. That's what, I think I said that in the first day here, right? If you think you're an engineer, and you haven't taken anything apart to see how it works, you're not an engineer. You have no aptitude for it. You think that that's something cool that you could explore, but it's not your nature. If you're not disassembling things to see how they work, so that eventually you can come up with something new, which is what engineering is, I'm not asking you to go and disassemble an airplane or a space shuttle, right? You can then open up your engine and see what's in there and understand how that works, because that technology is 100 years old now. We've been burning and exploding dead plants and animals in the engine block for hundreds of years, and that technology should be dead for a long time. One of the most inefficient machines that we have, 27% efficiency. You take any supercar that they call a supercar, they're going 200 miles per hour, that speed is pathetic, that's nothing. That 200 miles per hour is nothing in terms of the speed. And it's working on a principle that discovered 150 years ago, whatever. And it's still the main thing that propels. So yeah, we have the electric car now by Tesla and others are popping on, but we need engineering. Yeah, no. Yeah, you just put the new chassis on the outside and put the new sticker and says, wow, so this is now new and better, and put the additional button that eventually will break. It's cost money to fix. So
I feel like you would want to test them.
I do. Well, I will have tested in some few years, but the trick is that, you have to understand how things work.
Yeah.
You have to find your hole. You have to be involved, engaged, interested in something genuinely to be successful at it.
True.
And you program every day?
Sometimes.
You know how to program.
I just do a pattern. And
I watch other people code. I watch them type. I don't look at what they're typing, but I watch them typing.
Exactly.
I'm a great coder. I promise.
That's how though.
I was working on Samsung Teams, but then I gave up on it.
See?
It just comes.
That's the spirit. All right, let's take a look at this derivative together. Took a little detour over here. So vertical asymptotes will be preserved. The location of this vertical asymptote is a -2, and it will stay there. If you carefully observe this piece to the left of the function, we see that all of the slopes are positive slopes. So the derivative for this piece must be pretty much the same thing. Just going to draw another red line above the x-axis. Note that, so I'm just going to draw something you have to look to see. On this part of the graph, note how the original function in black is leveling off to go and become horizontal at infinity. When function is horizontal, it has 0 slope, which means derivative would be 0. So it matches for them to have the same behavior going towards negative infinity. Now, looking at the top, you have the same behavior. The black line, which is the original function, is going to be almost vertical, which says infinite slope, which the red line would match at -2. Moving to the other side, observe that the function is negative. So observing a negative slopes, sorry, we're observing negative slopes, so that means that the derivative will be negative. So we are expecting to see this kind of behavior on the other end, because all of the slopes are negative.
No, looking at the slope bars, isn't it going up?
The slopes are going down. See, each tangent line looks like this, right?
Yeah.
That's a negative slope, which means that the y values of the derivative have to be below x-axis, because that's where the negative numbers are.
Okay.
And then we have the 0 piece. We have the 0 piece here. And then we have a -1 piece, which goes like that. So I hope that your derivatives looked like this once you drew them. And this type of analysis is very important, because it gives you information on change quickly. The graphs could be deceiving, and in that case the derivative might show, derivative would show the change faster and more accurate. Well, maybe not more accurate, but it will be easier for us to read. Take, for instance, stock market. If you are a broker and you are that's almost obsolete as well, because bots are doing that today. But let's say you're observing a stock and the price is radically changing, and the original graph, you know how they look like, is zigzag, right? But the trick is that the zigzag, you have to be very careful on the left whether the zigzag is happening on the level of 1 cent, 10 cents, $1, $10, right? $100. So the stock will rise and fall and rise and fall rapidly. And then you always have to be mindful of the units on the y-axis. But if you observe derivative rather than the stock behavior itself, as soon as you see the derivative going down, or the negative below x-axis, that means that the stock is experiencing negative gains, so you're losing money. So if you observe the derivative right here, right? Over here I'm not gaining or losing money, so that's why the change is 0. I am losing money here, and look, all of the pieces where I would be losing money, they're below x-axis. All of the pieces where I'm gaining money, they're above x-axis. So it's much visually faster for me to look at the graph and locate whether it's something is just above or below x-axis. Because anything above x-axis, I'm making money. Anything below, I'm losing. I can make split-second decisions upon glancing on the graph, rather than watching every single zigzag, which way it goes, and then what are the units and dimensions and break, right? This is simplifying that fast decision, making money, losing money. So where is it now? It opens at 9 and closes at 4, and where is the piece of the line? So you can see that on the upper graph as well, right here. Clearly making money, making money, making money. So all of these are up above the x-axis. Here's me losing money right there. Look, it's below. And then I'm making money again from here up. I'm making money, so it's up positive. So the derivative can very quickly tell us the change, and whether it's a positive change or the negative change. Now that is going to be clearly tied to increase and decrease. So you see that every time when function is increasing, the derivative is positive, which means it's above x-axis, and every time when the function is decreasing, the derivative is negative, below x-axis. You can also draw these little slopes and slopes will quickly tell you whether you are looking at the positive or negative derivative. Now, in the textbook, they have more functions for you to consider. They all look pretty much the same, just the different iterations. And there is another theorem. Again, this is not an honors class, so we are not going to prove this theorem, but it's worth mentioning that if the function is differentiable, it is continuous. Remember how I said that for continuous functions, we find the continuity at the point, and then the global continuity states that if the function is continuous at every point, the function is globally continuous? Well, you can check all of the infinity of the points. Now, this theorem helps us a lot because this theorem says if you can take the derivative of the function, it's continuous. So I'm just going to write, this is a major theorem that helps us a lot in later on in theoretical mathematics and so on. So if function f of x is differentiable at a, then f of x is continuous. At a. This also helps you with understanding that the vertical asymptote locations will be preserved. So you know that the vertical asymptote is preserved. So for, let's say, 1 over x, right? It remains at 0, and so on. Now, this theorem does not work backwards. It only works this way. If the function is differentiable, then it's continuous. There are certain continuous functions which are not differentiable, which makes it that the backwards of this one doesn't work. Yes?
By differentiable, do you mean has a derivative or able to have a derivative?
Yes, has a derivative at any point. So to further bring this, so 1 over x, for instance, is not differentiable at 0. So 1 over x looks like this, and we see the vertical asymptote at 0. So this is f of x equals 1 over x. Now, its derivative, I will tell you now because we don't know that yet, is negative 1 over x squared. Now, if you look at that graph, it looks like this. So we see that the location of the vertical asymptote remains in the same spot. Now, this is one example. This holds for everything. But the vertical asymptote is preserved at x equal to 0. And we also see that the function was not continuous and not differentiable at 0. And that holds for the derivative as well. And so now if you try to flip this around, it's not going to work because you have continuous functions which are not differentiable. For instance, absolute value of x is not differentiable at 0. It's continuous function. So if you think about this, absolute value of x, there it is. And if you draw its derivative, you see, it's not differentiable at 0 because that is the location where derivative, right, the left side claims that the derivative is -1 because that's -1 slope, and from the right side the derivative says +1. But you can't be -1 and +1 at the same location, right? So we put the open circle on one of them here because this continuous function creates a discontinuous derivative. So we say that this function is not differentiable at 0, but it is continuous. So continuity does not imply differentiability, but if the function is differentiable, it is continuous. So that's one of the major theorems. And that's the end of the section. So understanding that if there is no change in the function, the derivative is 0. Understanding that for linear pieces, the slope is the derivative. Understanding that vertical asymptotes remain in their spots. Understanding that every min and a max is the x-intercept for the derivative, because it will have horizontal tangent line that has 0 slope. Understanding then decreasing functions give us negative derivative, increasing functions give us positive derivative, and how to draw these lines, and connecting differentiability and continuous in sense where if the function is differentiable, it is continuous, and it doesn't have to work backwards. Where I showed you the counterexample that the backward statement does not hold all the time. It does hold sometimes, but not all the time, so you can't call it a theorem. You have to prove that for each individual case where it works, but it doesn't work in general. And that takes care of 3.2. We'll take a short break, and I will take care of the exam review.